Hello, hello, it is me, Ugo, and this is the umpire for light bulb. Okay, yeah. So this problem, pretty simple, I think. Well, not simple, but I guess it kind of is. There's a nice trick to it for the optimized version, but let's not get into that yet. So basically, we're given n bulbs and a list. Well, not n bulbs. We're not giving n bulbs. We're given a list of bulbs that are one indexed. We're not given the bulbs. We're given a list of like our action, which is flipping them off or flipping them on. I mean, not off. Sorry. um, so basically, what we're doing is we're given a list of numbers that are one indexed, so from 1 to n inclusive, and it's going to contain every bulb that we're working with or that we have. So it's going to be 1 to n inclusive, and yeah, so the list that we're provided represents the light bulb that we're turning on. So in this case, we have 2 at the start, so we turn on the second light bulb. We have 1 at the start, or the next number is 1, so we turn on the next one. Now the trick here is, or the big thing that we have to worry about is when we have a sequence of consecutive on, or light bulbs that are on, that are connected all the way back to the first one, that causes us to have blue lights. So blue lights are a third state where basically all lights before it are on. So in this case, we have 2 that's on, and then when we turn on 1, we have 1 and 2 that are on, and there's no more before it. So these 2 end up turning to blue lights. And then we have 3 after it. So we have 3 after it. The ones before it are all blue. So this one becomes blue. Then we have 5 at the after that one. 5 does not have one that connects it to the blue ones. So it stays just on and not blue. And then finally you do 4, and 4 will give you all of them being blue. So what we're looking for with this is actually we're looking for the number of times all of the bulbs that were on were blue. We're not looking for the total number of blues that there are, because at the end of the day, it'll always be all of them. What we're looking for is the number of times all of the lights that are on are blue. So in this case, this one has 1 on, but it's not blue, so this one doesn't have any. This one doesn't have any on. This one does have 2 on, and they're both blue. There's no normal ons, so that means that it matches the condition that all turned on bulbs are blue. So that will count as 1. And then we look at the next one. All of these ones that are on are blue too. So then we add another one. Then we check this one. This one has 5. 5 is not blue, but it is on, so it fails to meet the condition that we need to increment, or for the counting of all turned on bulbs being blue. So we don't count this one. And then finally, the last one has all of them being blue. So that causes us to have one case, or one moment, a second moment, and a third moment where all of the lights are blue. And that will be our output, the number of times that all of the turned on bulbs are blue. So, yeah. To approach this problem, what I saw was basically, since everything before the current bulb has to be blue, for the current bulb to be blue, then we can just ignore it. Because since we start off with all bulb being off, that means that if we're at a bulb that is blue, that must mean all the bulbs before it are on and have been visited and will not be visited again. So we can we can just basically toss them aside. We don't have to worry about them. What causes the current bulb to be blue is being adjacent to a blue bulb. So in this case, if we look at it, we have 4 here. 4 is adjacent to 3, which is blue. So what we can do is we can look for, or we can check if the current bulb we're on or that we're about to turn on is adjacent to the last or the rightmost blue light bulb that we've seen. Then that means this one will be blue when we turn it on. And we have to check if the future ones, or the ones next to it to the right of the current one, are on. And if they are, then we're going to turn those blue repeatedly because now they're connected to the blue before it. So that's what happens here at moment 4. We have 4 that turns on and that turns blue. And then we check that 5 is on and that turns blue because it's now connected to a blue one. Now this felt recursive to me, but it wasn't. I just used a loop, a normal one, but it felt recursive because you basically just repeat the process over and over and over again until you reach a point where either you find an off or a bulb that's off, or you reach the end of the list. So that was my original approach or thought process, and I think I'll show that one first. Let me see, is it here? Yeah. So my thought process had the 3 states, and we're going to track them. The easiest way to do this is to just use an integer. So we could have 0 as off, 1 as on, and 2 as blue. However, I know that that is using magic numbers or whatever. I think that's the name of it. So let's see, magic numbers programming, right? Magic number is any of the following: a unique value with unexplained meaning or multiple occurrences that could be replaced with a constant. So it's gonna have these constants that would be 0, 1, and 2, and I think it would be better if we used an enum in that case. So I made an enum in Python. That was the first time I've done that. So that's what this is. We have off, which is 0, on, which is 1, and blue, which is 2, in a class, in an enum that's called bulb state. And we start off by initializing a list of off states. So they're going to have a list of bulbs, and all of them are going to be set to off. And we know that the list of the lights that we're turning on is the same length as the number of bulbs that we're going to have. So because of that, this will work. This will just create a n number of bulbs that are off. Then we'll create a variable which is blue occurrences. This will count the number of times all of the lights are blue. And then we have the last blue index. This will allow us to keep track of the last blue index because we don't have to worry about the prior ones because we know that all of them are blue. We just have to worry about the last one to check if the current one that we're looking at is adjacent to it. So we're going to keep track of the last blue index, and then we're going to keep track of the number of lights that are on. If this number is ever at 0, but we have a bulb that is blue, that means that we will have that means we found a moment in time where all the bulbs that are on are blue. However, that will only happen if the on counter is at 0. So what this one does is we first iterate through all of the indices that we have provided to us by the input lists. So all of these indices are one index and will represent which light bulb gets turned on at any moment. So we start off by checking first if the current index that we're at is to the right of the next index or the last blue index that we've seen. So if it's to the right of it, that means that we found an adjacent one. I set it to be equal to 0 at the start, so I don't have to do a check for the first element. Since it's one index, this makes it simpler. And it's only one little thing that we're looking at. Let me zoom in a bit. Because it's one index, it's more, we had to subtract by 1 when we're using the actual list, but that's fine. And here what we're going to do is we're going to set the current index that we're on to be blue if it's adjacent to the last blue index that we've seen. And then we're going to increment I over 1, so then we could check if the next one is on to turn blue. And that's what we're doing here. As long as I minus 1 is less than the length of the list, and the bulb that we're currently looking at is on, then we have to turn those blue. And that's because as long as there is an on state next to a blue state, we're going to have to turn it into blue. And so what's happening here is we're going to turn it to blue, so the bulb at the current index becomes blue. We decrement the on counter because we changed the one that's on to blue, so it's no longer on, and we can reduce the counter for on. And then we can increment I to move forward until we find one that fails one of these two conditions. So either we reach the end of the list or we find something that is not on. We will never find something that is blue. So I could have just done not off. But I thought being on would be more explicit, because all blue ones are going to be to the left of the last blue index that we've seen. And then we just update the last blue index to be I minus 1, because it will increment and it will only fail when it's not on, or if we're at the very end. So the last blue index will be the last blue index that we saw, basically. I mean, this is what it is. And then we just check if the counter for the on switch or the on bulbs is 0. If it is 0, that means that we don't have any ons, and that means we have a blue. The reason we know that there is a blue is because we have checked before this that this current index will be right next to a blue light. So even if it's the first blue one and that's the only one, there's still a blue, and if there's 0 ons, that means we have at least one blue in this case. So in that case, we're just going to increment the all blue occurrence. So we're going to increment this variable that represents the number of times all on bulbs are blue. If we're not adjacent to a blue light bulb, then what we're going to do is we're just going to set the current light bulb that we're looking at to on, and then we're going to increment the on counter. So if we look at this example at the start, the first condition would fail because the last blue index is set to 0 and 1 is off. So it is not, or well, the 2 minus 1 is not equal to the last blue index, which would be 0. So then that case will cause it to go down to the else statement, and it will be set to on, and the on counter will be incremented. So when we get to 1 next, we're going to check here. 1 minus 1 is equal to the last blue index, which is 0. And that causes this to be set to on, and then we go to the while loop. In the while loop, I minus 1 is less than the length because we're not at the end, and 2 is on. So in that case, what we do is we're going to change it to blue. We're going to change the state to blue, and then we're going to decrement the number of ons because now we have one less on. And then we're going to move forward 1. We check this one. 3 is less than the length of the list, or I guess 3 minus 1 is less than it, but 3 is not on. So in that case, what happens is we stop the while loop there, and then we break out. The last index of blue is now updated from 0 to 2, and then we move forward. Or, well, not move forward. We check if there is any ons because we decremented on counter after getting this one to 1. So it goes from 0, on counter is equal to 0 here, 1 here, and then back down to 0. In that case, we're going to increment all blue counter by 1. And yeah, the reason, or well, not the reason, this is an O of n time solution because we're not looking back at the blues anymore. We're just looking at the last blue index and seeing if we're adjacent to it. And then we're just moving forward until we either find the end of the list or first first off bulb. And because we're converting all of them to blue until that point, we're never going to be going back after that. So that light bulb will only be passed through once, or twice technically. It will not be passed through n number of times. This is because we're only going to pass through it once when we're turning it on in the worst case, and then turning it blue afterwards. So the worst case scenario is if we have 2, 3, 4, and 5, and then finally 1. This is because we go to 2, 3, 4, and 5. We turn each of them on. And then when we turn on 1, we're going to turn this one blue. Then we go to 2, we have to turn this one blue. Then we go to 3, turn this one blue, next and next and next until the end of the list. So that would make it O of 2n, but we ignore constants and time complexity, so it becomes O of n. The space complexity is O of n too, because we're creating a list of of bulbs that are off, and then we're turning them on to basically use them to do this. I went with this approach because it's like, it's what this is telling us to do. So it's like logically just stepping through what the problem told us to do, but it isn't the most efficient one or the most efficient solution because we don't actually need to use a list. But I like this solution because, well, I used an enum, so it's kind of clear what's happening. We're turning something blue, we're turning it blue, we're turning it on, we're starting them all off with off, and we're gonna just do that. I feel like this is readable, makes sense if you step through it. So yeah, and then the fastest solution is actually this one. I think it's just O of n. It's not O of 2n, so it's just twice as fast. And the other thing about it is it's constant space. It doesn't use a list. So what this one does is it also uses the all blue count, and it finds the rightmost blue blue bulb. So we're gonna have that index, and we're gonna have the number of times it's all the bulbs are blue. Then we're going to step through the number or the list that we're provided. And what we're going to do here is actually we're going to use enumerate to track the index that we have and the bulb number that we're looking at. This is important because we could take advantage of this to avoid having to do any of the list stuff. We're going to get the maximum of the rightmost bulb, the rightmost blue bulb that we have, and the current bulb number. So yeah, this one's important because basically if the bulb number that we're currently looking at from flips is like way far ahead, what's gonna happen is rightmost is gonna become the bulb number that we're currently looking at, and the index that we're looking at right here is going to just check, okay, are we one to the right of the current number of what's it called? The current number of bulbs that are on. If rightmost is not right there, then that means that we have a bulb that's on later on in the list, so we don't increment it. But if all of the bulbs that are on are before this rightmost point, then this condition will be true, and we will increment it because all the bulbs that are on are before the rightmost bulb that we have currently, and the rightmost bulb that we have currently is going to be basically the last blue bulb. and that will be the same thing. If we look at both solutions, this one had a 45%, 43%. I think it's still the fastest solution. I don't really see how you can do better than it. Maybe this actually. No, I think it's basically the same stuff. But yeah. And then my other solution was a bit slower, like I said, basically twice as slow. And it's not as memory efficient because it's of n space. But if we look at it, it does work. Same thing right here. Run it, it'll work fine. So yeah, pretty cool. Overall, both solutions work. This one's a little slower and more space consuming, but I feel like it's more readable too if you step through it. This one relies on, oh, not that one, but this one relies on like basically understanding that, or taking advantage of the rightmost blue bulb to figure out whether or not we currently have all the on bulbs that are available on or to the left of it. Sorry. But yeah, that's pretty much light bulb. Pretty cool problem. I liked it. I was surprised that this. Oh, what? Oh, it has a different name. Whatever, it's the same thing. But yeah, I like this problem. Nice O of n time, O of n space, and O of n time and O of 1 solution. So yeah.